Okay. Hello guys, good afternoon. Please type in your name in the comment box. Hi Sushant. Okay, so today we are going to discuss P block elements. Okay, so here in this P block elements, first we will discuss here carbon family. Carbon family. Okay, so in class 11th we have two groups which we have to discuss here in P block elements, that is boron and carbon. Right, so we are discussing carbon first, since this is a combined class with HSR students also, and for them I have already done boron family. Okay, so we are doing carbon family first and then we'll continue with boron. Okay, so they have exam also tomorrow, some lab exam they have, practical exam they have tomorrow. So once we finish carbon family, if they want they can leave also. Okay, that's why I'm discussing this carbon family first. You also have exam, right, Sushant, Ashutosh, RNR students? And the school is now it's closed, right? It's for preparation holiday. Hi Bharat, morning. Okay, so Monday onwards you have you have exams, right? School exam. Okay, last day for the school. So when can we have our class on Monday? Okay, Monday is chemistry. So when can we have our class on Monday? Sorry, on Saturday? Yes, we'll let you know after 22nd what is the schedule that I'm not sure with. Okay, we'll let you know, Bharat. That's what I'm asking, since I'm waiting for more students to join this. That's why I'm asking all these things. What you want me to do on Saturday? Hello, Advait. Can we do some basic revision of class 11 on Saturday since you have exams? No, Bharat, we cannot take organic problem solving. We have to take care of other students also. Yes, mostly we'll finish P block today, boron family and carbon. Like I said, we will not discuss everything. You have to study NCRT. Important thing we'll discuss today. Okay, anyway, so we'll figure it out what we'll discuss on Saturday. We'll let you know. So today we are going to start carbon family, right? And then we'll do boron also. So you see in carbon family, these are the elements of group 14. Group 14. I'm not sure with this, Ashutosh. Maybe, may not be. I'm not sure with this. Anyone told you this thing that we don't have class till March? Usually it happens every year. We don't conduct classes during exam. That's the thing, right? So that's the thing. Anybody told you this, Ashutosh? Okay. So you see group 14 and the elements of group 14 are what? The elements are carbon, then we have silicon, then germanium, tin, and in the last we have lead. Yeah, that's what. Let's see what happens. Anyways, so these are the elements of carbon family we have. Okay, so carbon is C, silicon is Si, germanium is Ge, Sn, and Pb. Okay, atomic number. What is the atomic number we have here? Atomic number, if we write down, that would be for carbon it is 6, for silicon it is 14, then 32 plus 18, 50 plus 32 is 82, right? So the magic number here is this difference is 8, then this difference is 18, 18, and here we have 32. So magic number of P blocks are 8, 18, 18, and 32. Okay, electronic configuration if you draw, right? So for the first one we can write 1s2, 2s2, 2p2. Or we can also write the configuration of helium is H, helium is 1s2. So helium 2s2, 2p2, right? Then we can write down the electronic configuration of silicon, that is neon 3s2 3p2, argon 4s2 4p2, krypton 5s2 5p2, 5s2 5p2. Then this is krypton. Then we have in the last xenon Xe 6s2 6p2. Right? One thing important here again, you have to understand this, that in germanium, what happens before this 4s, we have completely filled 3d orbital, 3d10, right? Similarly, in tin, before this 5s, we have completely filled 4d orbital, 4d10. Similarly, in lead, before this 6s, we have completely filled 4f orbital and 5d orbital, 4s and 5d10. And we know that this D and F orbital shows weak screening effect. So this thing we'll use later on in this chapter to explain the trends. Okay, weak screening effect. So these are the electronic configuration. Now you see few trends. If I discuss like few general thing, if I tell you, right, carbon, like from this electronic configuration, one thing is clear, that general electronic configuration, if I ask you for carbon family, it will be ns2 np2, right? N is the number of period, ns2 np2. For the carbon it is 2s2 2p2, since it is in the second period. Silicon 3s2 3p2, third period. 4s2 4p2, fifth, sorry, fourth, fifth, and then sixth, right? So okay, so now with this electronic configuration only, the trends, if you want to discuss here, few trends, that will be, first of all, we'll discuss oxidation state. Oxidation state. Okay, so in oxidation state, what happens? The carbon and silicon, okay, carbon and silicon shows +4 oxidation state, generally +4 oxidation state. Okay, but the other three elements, which is germanium, tin, and lead, they shows +4 and +2 oxidation state. Okay, so for germanium and tin, these three element shows +4 and +2, both oxidation state. But for carbon and silicon, it shows only +4. Right. What happens here, actually, you see, there is a term called inert pair effect. You know what is inert pair effect? What is inert pair effect? Do you know that? Tell me. What s orbital? All these s orbital, this s orbital also, this s orbital also, this also. Okay. See, that is not the thing. And this is important for a school exam also. They ask you this, what is inert pair effect? See, first of all, if I ask you, what is the order of shielding effect of orbitals? Okay. So, shielding effect for orbitals. It is maximum for S, then P, then D, and then F. Right? And usually we say what? D and F orbital shows weak screening effect or shielding effect. I have written here. Weak effect. D and F orbital. So when the electrons present beyond this D and F orbital, then those electrons are strongly attracted towards the nucleus, since because of weak shielding effect of D and F orbital. Okay, so what happens here, you see how this +4 oxidation state forms or get when these 4 electrons which is present in the outermost electronic shell takes part in the bonding. Okay, takes part in the bonding, right? So these 4 electrons, when it loses, then only it forms +4 oxidation state, and when only these 2 electrons take part in the reaction, that gives you +2 oxidation state of the element, right? So these oxidation state +4 and +2 depends on how many electrons present in the outermost shell takes part in the bonding, correct? So here you see what happens. That's why I have written 3d10, 4d10 and this here. What happens when you go from silicon to germanium, since we do not have d orbital present here or here, we don't have d orbital present, right? So what happens, these electrons and the inner orbital of these electrons are what? We have s here and here we have sp both. The inner shell orbital, this is the outer shell, right? The inner shell orbital, we have 1s2, 2s2, 2p6. Here it is only 1s2, right? So here we have s and p orbital. Here we have only s orbital, but both s and p orbital shows a strong shielding effect, right? That's why what happens, these 4 electrons present in carbon and silicon, right, is weakly bonded to the nucleus because of strong shielding effect of s and p orbital here. Since these 4 electrons are weakly bonded, so these two may take part in the reaction, and that's why the carbon and silicon shows +4 oxidation state. Is it clear? Clear, yes or no? Tell me. Clear, understood? Right. So now next what happens? So this is one thing. Why carbon and silicon shows +4 oxidation state. Now coming back to this germanium, tin and lead, what happens when this electron goes into 4s and 4p orbital? So before going into these orbital, electron has to fill this 3d orbital here. So the penultimate shell or the inner shell here we have is nothing but the 4d orbital. Correct. So the penultimate shell contains completely filled d orbital, which shows weak screening effect. So because of the weak screening effect of d orbital, these outermost electron, which is 5s2 and 5p2, is strongly attracted towards the nucleus. And this is true in the case of germanium also, tin and lead. Because we have 3d, 4d, 4f, 5d. Right? So because of the completely filled d and f orbital here, these electrons, which is s and p, two electrons in s, two electron in p, are strongly attracted towards the nucleus, and this attraction is more dominating over this s orbital than this p orbital. Because why? This orbital is closer to the nucleus in comparison to this p orbital, right? So what we can say, if in the case of germanium, tin and lead, these two electrons which is present in p subshell, p orbital here, these electrons and these electrons, when these electrons it donates, it forms +2 or oxidation state and +2 oxidation state here. But comparatively, electron present in s orbital are strongly attracted towards the nucleus. That's why it is very difficult for these elements to lose electrons present in s orbital, and hence they have difficulty in the formation of +4 oxidation state. Is it clear? Both electrons in s and p orbital is strongly attracted towards the nucleus as compared to the electrons in carbon and silicon. But when you compare the electrons of s and p orbital, s will be more tightly bonded to nucleus than the p electrons. Correct? So what happens because of this d and f orbital? The two electrons present in s orbital, or in other words, we can say a pair of electron present in s orbital is become inert towards the bonding. Correct? Because of weak shielding effect of d and f orbital. So a pair of electron which is present in s orbital becomes inert towards bonding. Hence, we call it as what? Inert pair effect. Understood? Clear? Yes, tell me. Understood? Yeah, I'll just give first to try to understand what I'm saying. Definition I'll give you. Right? So what happens here? What happens here? The pair of electron becomes inert towards the bonding, and hence we are calling it as inert pair effect. Why it happens? Because of completely filled d and f orbital present in the penultimate shell. Okay, this is what inert pair effect is. Now definition, if you want to write down here definition. Inert pair effect definition you write down. It is the reluctance of ns2 electron. It is the reluctance of ns2 electrons reluctance of ns2 electron to unpair and participate in chemical bond formation. It is the reluctance of ns2 electrons to unpair and participate in chemical bond formation, comma, which arises due to which arises due to the presence of arises due to the presence of weak shielding weak shielding fully filled d or f electrons, fully filled d or f orbital, you write down fully filled d or f orbitals between the valence electron between the valence electron and valence electron and the noble gas core and the noble gas core, core, right? These are noble gas. So valence electron is 6s2 6p2 and these are d and f orbital fully filled. Okay. Okay, so what happens you see here, this is important now. As we go down the group from down the group from germanium to lead, Pb, what happens? The tendency to form +2 oxidation state increases. Write down here, tendency to form tendency to form +2 oxidation state increases and tendency to form +4 oxidation state decreases. Right? So what we can say, one thing is here you write down, next slide I use, stability order. Write down stability order in this only. For +4 oxidation state, the stability is this. It is most stable in germanium, then Sn +4, and then Pb +4. Because +4 oxidation state increases down the group, tendency to form, right? But for +2, the stability is reverse. Ge +2 is minimum, then Sn +2, and then Pb +2. This is the stability order of the two oxidation state we have. Okay. Now you tell me one thing here, that for germanium you see germanium is more stable in +4 oxidation state, right? So whenever you have Ge +2, it has tendency to convert into Ge +4, right? Similarly, lead is more stable in +2 oxidation state. So whenever you have lead Pb +4, it has tendency to convert into, I'll write down this sign. It has tendency to convert into Pb +2. So what is this behavior and what is this behavior? Tell me. What is the first one and what is the second one? What kind of behavior is this? Oxidation and reduction. This part, oxidation number is increasing. So what happens? Germanium is getting oxidized. Is getting oxidized. Right? Means here it is behaving as a reducing agent. Listen to me carefully here. Don't get confused. Reducing agent. Right? And this is what lead Pb is getting reduced, right? So we call it as what? Getting reduced. So it is an oxidizing agent. Oxidizing agent. Okay. So if I write down here, tendency to behave as a reducing agent. Tendency to behave as reducing agent, right, will be more for germanium, then Sn, and then Pb. Here I will write down tendency to behave as oxidizing agent is minimum for germanium, then we have 10, tin, and then we have lead. So Pb plus 4, you can say it is strongest oxidizing agent. Remember, I am writing down oxidizing agent here, right? And this one is the strongest reducing agent. This one, sorry, this one is the strongest reducing agent. This property is very important. Okay, you must remember. So when you write down PbCl2, PbCl4, it always has tendency to convert into PbCl2 because here the oxidation state is +4 and here it is +2. And we know lead in +2 oxidation state is more stable. That's why the answer will be this. Right? So if I write down here the last thing, like for all the elements, we have carbon, silicon, germanium, tin, and then lead. Carbon shows only +4 oxidation state. Silicon can show +2, +4, but generally it is +4 only. Germanium can show +2, +4. Tin can show +2, +4, and lead will show generally +2. So in all these oxidation state, this is only possible oxidation state for carbon. For silicon, +4 is the most common. For germanium, +2 is the most common. Then tin we have +2. And then for lead we have +2 itself. Note germanium can have +4 also. Both oxidation state for germanium is common. But this is the important part which you have to memorize as far as the oxidation state is concerned. Understood? Okay. Next, write down what about the covalent radius, the trend of covalent radius. Covalent radii. So that's the same thing as we go down the group. As we go down the group, it increases because we are adding an extra cell of extra energy shell into it. So carbon will have minimum, right? What is the order here we get? So write down the statement here first, then we'll see. First write down the statement. In this group, in this group, there is considerable increase in this group covalent radius. Write down the statement. In this group, there is a considerable increase in the covalent radius from carbon to silicon and thereafter from silicon to lead and thereafter from silicon to lead there is a small increase in radius is observed. Sorry, silicon to lead, a small increase in radius is observed. A small increase in radius is observed. This is the statement for covalent radius. From carbon to silicon, first of all, down the group it increases. Okay. But from carbon to silicon, the increase is much larger than from silicon to lead, whatever the increase we have. Okay. Now the reason for this word, this is due to the addition of a new shell in each succeeding element that we already know. The increase in radius from silicon to lead is small. Why? Because of the ineffective shielding of valence shell of electron. That also we have discussed. Since as we are going down the group, the electrons are going into d and f orbital, which has weak spinning effect, and hence they appear strong attraction towards the nucleus, and hence the increase in size decreases comparatively. Understood? See, Gargi, electronegativity is the relative concept. Okay, we always define electronegativity in a bonding state. You see, what happens if you write RCl, correct? RCl. Here we say because of electronegativity, here we have partial negative, partial positive charge, right? But when you have an atom, chlorine, in this free state for an atom, we cannot define electronegativity. It is not possible because electronegativity is what? It is it is a relative concept. It is not absolute, right? Carbon when attached with chlorine, right? So here the carbon having positive charge. When carbon is attached with, right, hydrogen, in that case carbon has slightly more electronegativity, so carbon will have then slightly negative charge over there. So it means what? This electronegativity is a relative concept. It won't it We can only explain electronegativity between the two atoms. For an atom which is independent, free, we cannot define electronegativity. Understood? Clear? Yes, electronegativity we can only explain in bonding state, to what element it is bonded with. Right? So here the point, we are talking about the covalent radii of an element. So electronegativity does not have any effect. Okay, so the reason is same, extra shell of electron we are adding, and then as we are moving down the group, electron is going into d and f orbital, which shows weak screening effect. So there will be a little bit of contraction in the size. Hence the increase in covalent radii from top to bottom decreases, right? Initially the increase will be more, then it will be comparatively less, right? Next, write down ionization enthalpy. Tell me the order of ionization enthalpy. Increases down the group. How? Okay. You see, the first of all, write down the order of ionization enthalpy. It is maximum for carbon, then silicon, then germanium, and then lead, and then tin. This is the exception, you can say. Lead has more than tin. Okay, so first of all, you write down, this is the trend. Now you write down few points here. First of all, you write down the first ionization enthalpy of group 14. The first ionization enthalpy of group 14. So IE1 of the elements of group 14. The first ionization enthalpy of group 14 elements are higher than that of higher than that of the corresponding elements of group 13. What is the meaning of this? If you compare the first ionization enthalpy of carbon, it is more than to that of boron. Silicon, it is more than to that of aluminium. This is the meaning of this point, first of all. Okay, we cannot compare these two or these two. It is then factual. We have to see the energy involved here, then we can say. Okay, but this is one thing. Now for this order, you see what happens. Write down, as we go down the group, the first ionization energy decreases, but the first ionization energy of lead is slightly more than to that of tin. Right? The general trend of, don't write this, just you listen to me. The general trend of ionization energy is what? As we go down the group, ionization energy decreases. And why it happens? Because the size is excuse me, because the size is increasing, right? So size has an important role here, because according to size only we have electrostatic force of attraction between the nucleus and the electron that actually defines or explains the ionization energy, right? So as we go down the group, you see we have a factor which we call it as inert pair effect, and because of inert pair effect, the size starts, the difference in size from germanium to tin is not, germanium to lead is not that much high. It is increasing, but that the gap is not no as high as it is in carbon and silicon. Correct? So size is getting contracted as we go down the group. That's why in case of lead, the ionization energy is slightly higher than to that of tin. So we have a little bit of irregularities in this order, in this trend. That is most important. You must remember this trend. Understood? Yeah, you can say that, but it is an exception actually. Just a second. Hello. Yeah. Hello. Yeah. Speaking. Calling from? Yes, bank. Yeah, tell me. Oh, no, no, I'm not interested. No, I have already, so I don't require it now. I have already the bank's card, so I don't require it now. If you want to give me the information about the benefits and all, you can call me tomorrow. Right now, I'm a bit busy. Okay, so you can call me tomorrow 11 o'clock. That would be fine. Okay, thank you. Okay, so this is the trend we have. Correct? So you must remember these values, exceptions that we have here. Next, write down electronegativity. Write down quickly. Electronegativity, as we go down the group, electronegativity decreases. Right? No, it's not. There is a change here a bit. Okay. Write down electronegativity first. Don't write down the group, it decreases. So for electronegativity, you see the general trend is what? General trend is down the group electronegativity decreases. Now what happens here in electronegativity, write down, as we go write down, the electronegativity decreases from carbon to silicon and remains constant from silicon to tin, and then slightly increases from tin to lead, Pb. Right? Generally, what happens? We say it decreases from. There is one more thing which is written in some other book. Decreases from carbon to silicon. Then after silicon onwards, silicon to lead, it is almost same, remains same. This is also written in some of the book. So this also you can consider if option is like that. Okay, these two things. So there's a slight increase, but that increase is not that enough. Okay, so in some book they have written this also. and some book they have written this also. So any one of these you can consider according to the given option. Okay. Right. Again, the reason is same because of the filling of d electrons in germanium and tin, and in lead we have f electrons also and d electrons also. That is the reason we have here. Okay. Next, write down metallic character. What is the order of metallic character? General trend is what? As we go down the group, electron enthalpy decreases, metallic character increases, and what happens? Electropositive nature also increases, right? In this you write down as we go down the group, the metallic character increases. As we go down the group, metallic character increases. Okay. Carbon, here you see this carbon and silicon, these are actually non-metals, right? Germanium is metalloid and tin and lead are metals, soft metals. These are actually metals, and that is soft metal. The reason behind this is what? As we go down the group, we have less effective nuclear charge, and the number of available orbitals also increases with increase in size of the atom. Okay, so the thing is because of less effective nuclear charge. Okay, one more point to write down. The elements of group 14, if you compare this character with group 13 and group 14, the elements of group 14 are the elements of group 14 are solids, and they are more electropositive and metallic, and they are more electropositive and metallic as compared to the elements of group 13. They are more electropositive and metallic as compared to the elements of group 13. Okay. Next one, write down tendency to form multiple bond. Tendency to form multiple bond. This is again important. Okay, write down. The first type of bond you write down here, which is p-pi bond. P-pi, p-pi. So write down this quickly. Carbon has a strong tendency to form p-pi bond. Carbon has a strong tendency to form p-pi bond with other elements of similar size. This is due to other elements of similar size means what? Other elements of similar size means what? We can have C double bond O, C double bond N, like this. Okay. C triple bond N also you can write, NH. C triple bond N also you can write. Right? So carbon has strong tendency to form this kind of p-pi bond with the elements of similar size. This is due to the small size and this is due to the small size and high electronegativity right, small size and high electronegativity of carbon atom. Next line, as we go down the group, the tendency to form p-pi bond decreases as we go down the group. The tendency to form p-pi bond decreases as the size increases and electronegativity decreases. Right, so it is basically when you talk about silicon with oxygen, nitrogen and all. So this has, you see here, the thing is here we have 2p orbital. Here also we have 2p orbital. All the elements here has 2p orbital. And that's why the lateral overlapping, we have good lateral overlapping here over here. But in case of silicon, germanium and all, we have 3p, 4p like that the orbital. So overlapping of 3p and 2p orbital, 4p and 2p orbital is not that possible. Yeah, that's what. The effective overlapping is not there and hence p-pi bond does not form. Okay. Now the second type of bond we have here, which is p-pi d-pi. P-pi d-pi. Right now, since carbon does not have d orbital, since carbon does not have d orbital in its valence shell, in its valence shell, it does not form p-pi d-pi bond. It does not form p-pi d-pi bond. But other elements of group 14 has tendency to form p-pi d-pi bond. right? So on the basis of this only, we have examples, and I think I have done this example. And this kind of bond, p pi d pi bond, is very silicon has very strong tendency to form this kind of bond. Like on the basis of this only, if I write down this example, SiH3 whole thrice N and CH3 whole thrice N. Which one is more basic here? Which one is more basic into these two? Which one is more basic? CH3 whole thrice N. Yeah, you see, what kind of base is this? This is Lewis base, right? Electron pair donor. So what happens here, you see, this has lone pair and this also has lone pair. But since here we have silicon which has vacant d orbital, the silicon has vacant d orbital. So this lone pair is donated to this vacant d orbital of silicon to form p pi d pi back bonding. Okay, and hence this lone pair is not available here, and hence it is not a base, weaker base. Yeah, but here since carbon does not have d orbital, no d orbital, so this lone pair is available here. So it can donate to the other molecule. So this behaves as a Lewis base. Understood? Yes. Understood? This is important example. Okay, must remember this. Okay. Next, write down reactivity towards oxygen. Reactivity towards oxygen. Write down the elements of group 14. The elements of group 14 when heated with oxygen. The elements of group 14 when heated with oxygen forms an oxide of forms an oxide of MO2 type. MO2 type and MO type. This is, as you can see, it is dioxide and this is monoxide. One note you write down here, All these small notes points are important. Write down SiO exist only at high temperature. Only at high temperature, where it is reduced by the where it is exist at high temperature. Just a second. Where it is formed by the reduction of SiO2 dioxide with Si, silicon itself. So the reaction will write down SiO2 plus Si gives you 2Si only at high temperature. Next, reactivity towards water. Reactivity towards water. Write down carbon, silicon, and germanium carbon, silicon, and germanium do not react with water. Do not react with water. Okay, Sushant, no issue. Carbon, silicon, and germanium do not react with water. However, on red heating means what? Strong heating also you can assume at high temperature. However, on red heating, these elements except lead, important this one, these elements except lead decomposes steam, except lead decomposes steam. You see carbon solid form plus H2O plus H2O on red heat gives CO plus H2 gas. Si solid reacts with 2H2O. On red heat, it gives SiO2 plus H2. Sn solid plus H2O gives SnO2 plus H2 gas. One note you write down here. One note you write down. Lead is not attacked by. Lead is not attacked by. Is not attacked by pure air-free water, pure air free water, except at boiling point, except at boiling point, except at boiling point. Next line, it is easily corroded by water. It is easily corroded water containing dissolved air. Containing dissolved air, forming lead hydroxide, forming lead hydroxide, lead hydroxide, which is soluble in water, which is soluble in water. This property you have to memorize, which is soluble in water. This reaction you write down 2Pb plus 2H2O O2 gives PbOH whole twice. Soluble in water, this one. Just last one point to write down, the solvent action of water. The solvent action of water is known as plumbosovalency. BOSO, plumbosovalency. Nothing we have to understand here. The point here it is what? That lead is generally not attacked by pure air-free water, except at the boiling point. What happens if you have air dissolved in water, right? And that air contains oxygen. So this oxygen is coming from air. If water contains air in it, right, and when it reacts with lead, it forms PbOH whole twice, which is a water soluble. Right, this is it we have. So the point is all these elements reacts with water, but lead generally does not react with water. Right? It reacts with water, but that water should be pure and air free. Right? If it is not air free, then it forms PbOH whole twice, which is again water soluble. Right? Now we see some general characteristics of compounds. Okay, we'll see the compounds of this group and its characteristics. The first one you write down, hydrides. Hydrides, write down. These elements forms covalent hydride covalent hydrides like we have for carbon. Ashutosh will discuss this in the last. Okay, let me finish this first. The hydrides of carbons are what? Alkane, alkene, alkynes. Correct? We already know this. Hydrides of carbons are alkane, alkene, alkynes, aromatic hydrocarbons, and all. Write down few points into this. Write down germanium hydrides are straight chain compounds. Straight chain compounds. Write down the hydrides of tin. The hydrides of tin, we call it as stannine. Hydrides of tin. Stannane. Stannine. For germanium, we call it as germanium hydrides, or we also call it as germanes. Both are same thing. This stannine you write down, these are less stable and strong reducing agent. Next, write down. This is done. Next, write down uh, acidic character of oxides. Oxides we have already discussed that it forms two types of hydride. One is mono and other one is dia, MO2 type. Okay. Write down as we go down the generally we discuss about dioxides, which is generally more stable state. Write down for dioxides as we go down the group. For dioxides as we go down the group, the acidic character decreases. Acidic character decreases and basic nature increases. Right? Down the group, acidic character decreases and basic character increases. So if I write down CO2, SiO2, SnO2, and PbO2. So down the group, acidity decreases and basicity increases. Can you tell me the reason for this? Not stability, it is acidity. Acidity decreases. Anyone, can you tell me the reason? Yeah, you can also say the accessible d orbitals to accept a pair of electrons, or you can also say as we go down the group. Oh, that is not true here. Correct. See, as we go down the group, d orbitals are there, and size also increases, right? So it can easily accommodate the pair of electrons, and that's why the acidity, basicity increases, acidity decreases. Okay. Next, you write down halides. Halides, you write down. Write down all elements of this group. Yeah, stability of +4 will decrease down the group. Write down all halides of, sorry, all elements of this group forms tetrahalides, forms tetrahalides of MX4 type. Tetrahalides of MX4 type. Okay, write down. Write down among simple tetrahalides, the fluorine, GeO has amphoteric character. It is not completely acidic or completely base. Right? Among simple halides, tetrahalides, the tetrafluorides of carbon, silicon, and germanium. The tetrafluorides of carbon, silicon, and germanium are gases, exist in gaseous form. However, this SNF4 and PbF4 is are actually solids. Why? Because these halides are covalent in nature, and because of its covalent nature, it is a volatile gas. Not important, only the state sometimes ask gases or solid. These two halides have ionic character. This is also, you remember, ionic character. Okay. About tetrafluoromethane CF4, we'll discuss few points, just few facts we should know. First of all, since it is tetrahalides, all atoms are sp3 hybridized. For halides, carbons are sp3 hybridized. Okay. CF4, you write down, it is carbon tetrafluoride. Write down, it is exceptionally unreactive gas and highly stable. CF4, you write down, it is exceptionally unreactive gas and highly stable. Right. The preparation method of CF4 is what? When this CO2, carbon dioxide, is allowed to react with sulfur tetrafluoride, it gives CF4 and SO2. Displacement kind of reaction it is. This is the laboratory method of preparation. Laboratory. Now the industrial method is what? We use chlorofluoromethane, right? Which is, CF2 dichloro. When this is allowed to react with fluorine itself, it forms CF4 and chlorine evolve. Now, why we are discussing this here? Because this is actually a monomer CF4, right? Its dimer, if you see CF4, the dimer of CF4 is, okay, just a second. It's not, it's dimer, just a second. See, we get CF4 carbon tetrafluoride, but there are also possibility of getting, of ended up getting hexafluoroethane into this, which is nothing but C2F6. Or we can also get tetrafluoroethane, which is C2F4. Hexafluoroethane or tetrafluoroethane. Now this C2O4, which is tetrafluoroethane, when it is polymerizes to C2F4N, this we call it as polytetrafluoroethylene. Okay, this is what polytetrafluoroethylene, PTFE. Polytetrafluoroethylene is the polymer of tetrafluoroethane. Now, few uses of this is important. That's why I have given you this. Uses of this, you write down polytetrafluoroethylene. Polytetrafluoroethylene uses, you write down. Write down. Used as, uses, you write down. Good electrical insulator. For coating non-stick pans and razor blade. For coating non-stick pans and razor blade. It is chemically inert in nature, heavier and more dense. Inert in nature, heavier and more dense. Okay. Now the last compound we'll see here. Write down carbonates and bicarbonates. Just a second, just a second. This is not required here, I guess. It is carbonates. Yeah, this we have done. Not required. Let it be. Okay. So the next thing we'll discuss here, that like we have we have now discussed the general trends, some compounds, halides, hydrides, okay, oxides, the acidity of oxides, reaction towards water, all these things we have discussed, inert pair effect. Okay. Now there are few compounds which is important here to understand, few reactions into that we'll discuss, and then you can follow NCRT actually. Okay. The first compound you write down, that is of these elements are, you write down heading, you write down polyhalogen compounds. Few compounds we'll discuss, and the heading you write down polyhalogen compounds. The first compound in this, write down dichloromethane. Dichloromethane, which we also call it as methylene chloride. Methylene chloride. What is the chemical formula for this? Can you tell me? Methylene chloride. What is the chemical formula? CH2Cl2. Correct. Dichloromethane. Okay. You see, it is prepared by direct chlorination of methane, and we have done this in organic. Cl2 H nu, right? And then with Cl2 H nu, we'll get CH2 Cl2. Okay, CH2 Cl2. The another method of preparation is what? When chloroform, write down, we can also prepare it by the reaction of chloroform with metal and acid. Reduction of chloroform chloroform with metal and acid, which is nothing but Zn plus HCl, metal and acid we use. What is the formula of chloroform? Do you know the formula of chloroform? What is the formula? Chloroform is CHCl3. Okay, CHCl3. So when you do this reaction, CHCl3 reduction Zn and HCl. So it forms CH2Cl2 plus HCl. This is the two preparation method of dichloromethane we have, which is not that much important. What is the use of this? It is used as a solvent, inert solvent. We have already seen this. Okay, inert solvent it is. We can also use this as paint remover. Paint remover, metal cleaning, and finishing solvent. Finishing solvent, manufacturing drug. There also we use this as a solvent. Manufacturing drug. This is actually harmful for human also, right? Because it harms the central nervous system, right? Few things I'll just tell you, just listen to me. Okay. On exposure of CH2Cl2 in air, it leads to slightly impaired hearing and vision. Okay. So that's a harmful effect we have on human. Because of this, you can have nausea, dizziness, numbness, numbness in the fingers actually. Right? Direct contact with the skin, it causes burning sensation and mild redness of the skin will be there. If it direct contacts with eye, it will burn your cornea. Okay, so it is very harmful actually. Right? So we always use this whenever we use this in laboratory, we take a lot of measures. It can, it can possible. So it depends, like the exposure, to what extent you are in, um, influence of these things. If it is little bit, you will have slightly, burning sensation and all. But if it can burn, right, and if you have exposed to it to a very large extent, then it may knock people out. It's not a big deal. Right? Depends on what extent or what amount it is there. It depends on that. Okay, so these are the few uses and what we say uh, the harmful effects we have, which is actually used in school exam, board exam. Write down uses and harmful effects or like that. Okay, how it is harmful to human. This kind of questions for 1 or 2 marks usually they ask. That's why I have given you this. In JE they don't ask all this question. Okay, so the next compound you write down is trichloromethane. Trichloromethane. Trichloromethane is CHCl3, which is chloroform. Write down. It is used in the manufacturing of. It is used in the manufacturing of freon refrigerant. What is the refrigerant? It is used in the manufacturing of freon refrigerant. Freon refrigerant, which we also write it as F22. And the molecular formula is C2F2Cl4. This is also the same thing. It causes dizziness, headache, right? Uh, if you have exposure to this to a large extent, it may cause damage to liver, right? Kidneys. It is also widely used in anesthetic, like in anesthesia. For anesthetic purpose, we use this as anesthesia because of its toxic in nature. It is toxic in nature, right? But since it is toxic, so nowadays we don't use this as an anesthetic. It is again, how do we manufacture this? It is again manufactured by the chlorination of methane, right? So write down the single one line here. It is manufactured by the chlorination of ethane. Chlorination of ethane, and when it reacts with oxygen in presence of air, in presence of light, when it reacts with oxygen in presence of light, it forms phosgene gas. Phosgene gas. For example, you see CHCl3, when it reacts with O2 in presence of light, it forms phosgene, which is COCl2 plus HCl. This is phosgene, Gene. One more point to write down. When phosgene reacts with ethanol, when phosgene reacts with ethanol, it converts into diethyl carbonate. It converts into diethyl carbonate, which is harmless. So phosgene is this 2C2H5OH. HCl and HCl goes out, so 2 moles of HCl goes out, C double bond O, and this will join. Okay, you see this H and this Cl goes out, so it is joined with C2H5O, C double bond O, OC2H5 plus 2 moles of HCl we get here. So this phosgene gas, it is actually toxic in nature, right? So when it reacts with uh, ethanol, it forms harmless diethyl ketone. This is again one reaction we have. Write down. It can also be prepared by hydrolysis of chloral, hydrolysis of hydrolysis of chloral by CaOH whole twice. It can also be prepared by the hydrolysis of chloral by CaOH whole twice. Right? Now you see what is chloral here. Suppose we have ethanol CH3CHO. When it reacts with Cl2 in presence of CaOH whole twice, chlorination, then it forms Cl3C CHO plus 3 moles of HCl. So all this chlorine atom knocks out these hydrogen atom here and forms HCl. Just a second. Okay, I'll tell you what is the use for phosgene. Right? This we call it as chloral. Right? Now, when this chloral is allowed to react with CaOH whole twice, which is nothing but this, like this if I write down, plus we have Cl3C CHO, and we are taking 2 moles of this here. So Cl3C CHO, 2 molecules we have here. Right. So the product we get here is 2 molecules of CHCl3 plus HCOO whole twice Ca. So here what happens, this H combines with this CCl3 and knocks out as CHCl3. This is how we prepare chloroform, right? Now, like you said, what is the use of phosgene? Okay, phosgene actually used to prepare this CaOH whole twice with removal of Cl2. You see here, CaOCl2. I'll write down this reaction, which is probably this. This is phosgene, and when it is react with water, when it is put into water, it forms slaked lime, which is CaOH whole twice, and chlorine evolves here, chlorine gas, right? Which we further use here, chlorine gas, we further use here with ethanol for the preparation of chloroform. Further, if you react this with water, you'll get phosgene again. Few points you write down here. Like it is, few points you write down quickly. It is a sweet smelling, colorless liquid. It is a sweet smelling, colorless liquid which is immiscible with water, which is immiscible with water and miscible with organic solvent. Immiscible in water and miscible in organic solvent. Next line. It is slowly oxidized by air It is slowly oxidized by air in presence of light to a poisonous gas, in bracket you write down phosgene, to a poisonous gas, in bracket you write down phosgene. Hence, it is stored in colored bottles. Hence, it is stored in colored bottles, which is completely filled, so that air is kept out. Right? The bottle must be completely filled so that air is kept out. One important reaction of this I'll give you. One already we have done, that is iodoform reduced with silver. It gives you acetylene. 2 moles of iodoform is used. See, phosgene is a toxic gas. Okay, so like the chemical warfare. If you see, you must have heard that in somewhere in um, Iraq or Syria, uh, Russia has used some chemical weapon. You must have heard that in the news. Yes, all these things that I have given you now, it is for chloroform CHCl3, not for phosgene. Have you heard this? That Russia has used some chemical weapons against Syria, right? Which was not actually uh, right. It was just just an allegation on Russia that he has used. It is not. We are not very sure that he has used it or not actually. Okay, but the point is, what is that chemical weapons? Chemical weapons are those kind of weapons that we have, which when you explode it, some chemical reaction takes place and it releases a very toxic gas, which actually gives some skin sensation, some burning, and some dizziness, or some kind of nausea you will get. Okay, or even if it is more toxic, and if someone inhales, it will die also. So that, since phosgene is also a toxic gas, so we can use this into the chemical weapons. That's the thing. It's right. Chemical warfare, we use it. Okay, chloroform also we use, but it depends again, right? When the reaction takes place. So these kind of toxic gases we can always use in chemical warfare for chemical weapons. That's true. Right, but basically all those gases which are harmful for human, okay, those gases we can use, and there are possibilities that with few reactions this can give even more toxic gases. So those kind of reaction we use to we make them happen in chemical weapons. So this is the thing, right? So one reaction that you have already seen, when iodoform reacts with silver, it gives you acetylene, right? In preparation of alkyne, we have done that. Another reaction you see here. So in case of for instead of iodoform, we can also use chloroform over there. You'll get AgCl. Another reaction you see here, if this chloroform CHCl3 is allowed to react with HNO, nitrous acid, it gives you Cl3 NO2 plus H2O, right? This we call it as chloropicrine. PICRIN, chloropicrine, which is used as tear gas, which is used as tear gas. Okay, so this is it. Few compounds also we have discussed. Like you must go through with NCRT first of all the things you have to study from NCRT, and like I haven't discussed about glass. Okay, different types of glasses that you must go through with NCRT. Only composition things you have to memorize there. About glass you must study. Okay, and some behavior, anomalous behavior of carbon, behavior of carbon. Basically, NCRT you have to go through from beginning to end. Okay, and few more compounds are given in NCRT which you can go through, so that that may help you in the exam. Okay, the board exam that you have. But this is a glass thing. I have seen few questions onto this. They ask some Pyrex glass and all some composite types of glasses. Okay, so you just can go through. And there are probably few structures of the compounds of silicon also it is given. If it is not, you let it be, but you just go through with that. Okay, so this is it. We are done with this. One more thing I forgot to tell you. You have to go through with allotropes of carbon also. Diamond, graphite, no, buckyballs, fullerenes, all those. C60. It is given in NCRT. Okay, so that much is enough. Like if I give you now, I'll just dictate you the theory. So I am not giving you that because it is given in NCRT. You can go through with that. Okay, so allotropes of carbon is also important. Okay, fine, understood. Okay, good. We'll take a break now. Okay, I'm tired of continuously I'm speaking, right? So I'll take a break now. 10 minutes break will take. So it's already 6:10. We'll start at 6:20 or 6:12, something like that. 6:22. Yes, we'll take a break and then we'll start. Okay. Then we'll discuss geolites also. Okay, we'll take a break now. We'll start in 10-12 minutes.